This video is going to correspond more or less to the beginning of Chapter 3, and it's going to cover the basics of vectors. Now, something to notice is that the very beginning of Week 1 also talked a bit about vectors, and there's going to be a lot of overlap here. So I might not be going as slowly or in as much detail through this because there's already been a section of videos on it. But if you find this really repetitive, that isn't just you, you have seen a lot of this before. So if you feel really good about the basics of vectors, you might not need to watch these. But a lot of what we're going to be talking about, therefore, is review from what we did previously. And there's really two learning outcomes that I'm going to connect this to. Specifically, this is going to just be graphically working with vectors. And so vectors are therefore showing up a lot in our visual representations of physics, but also this is an issue of communication, that how you draw your vectors and how you represent your vectors in notation really has a lot of information in it, so it's important that that information is correct. So really briefly, I want to go through some notation issues here. So most of this isn't new, but we can be a little more specific now that we've seen some physics. So the first thing is that this vector here, when we write it this way, again, v typically is going to mean a velocity, and as you know now, velocity has a magnitude and a direction. So the magnitude of velocity we would just call speed, and that's what this v without the vector symbol would represent. So one thing, as always, to be careful is that if you just write v without the vector symbol, I might not know if you've made a mistake or not. So one thing you can always do is more explicitly use magnitude of the vector, and frequently we just use the magnitude, the symbol like this without the vector sign. So this explicitly means magnitude of the vector, which we usually just write this way. So now, here, this figure is saying the direction of the vector is this way. Obviously, you never actually draw that. That's just trying to point out that the magnitude is given by the length, right, from here to there, and then there's also a direction. So don't actually draw this. The last thing that's really important to realize is that this vector is only corresponding to one point. So when you draw a vector, the vector obviously has a length and it's over some linear distance then. However, the vector really only corresponds to this one point here, which is going to be the tail of the vector. So this is going to matter as we start to have figures where there's many, many vectors on the figure, and vectors start doing overlapping things and things like that. And what you have to remember is that this vector represents the value only at one specific point, this point here at the tail. So frequently we are simplifying things a little bit with vectors, and this shouldn't be too shocking. A lot of what we're doing in physics is simplification. So what this picture is theoretically showing you is the top-down view of a house, and Sam perhaps walks out of their front door, and maybe they take kind of a curvy path and eventually end at this point. So what we're trying to look at here is the fact that Sam has an initial point and a final point, and so we create the displacement vector between these two, and we're not actually saying that Sam walked in a straight line from the initial to the final point, simply that the displacement vector represents the distance between them and the direction, and we're not actually worrying about the specific path taken. So when we say displacement, this is what we're talking about. There's going to be some other vectors that act similarly to this, but again, in this case, we're simplifying a little bit. Another thing that's been stated before, but now we have a little more information, so hopefully we can do this in a more clear way, is that two vectors can be identical even if they're in different locations. So in this case, we have a house for Bill and a house for Sam. They've both left their front door and they've walked the same distance and the same direction. Now, obviously, they started in different places and they ended in different places. So for instance, I can draw a origin of my coordinate system here, and I can imagine drawing position vectors to this initial point here, Bill's initial point, and another position vector to this final point, Bill's final point. And you can see that clearly each of the final positions is different and each of the initial positions is different. However, when we talk about the displacement vector, we could say, for instance, the displacement vector for Sam is equal to the final position of Sam minus the initial position of Sam, and so on, same for Bill, and these displacement vectors are in fact equal. So keep in mind that all that matters for a vector is its magnitude, its length, and its direction. So even though these two vectors start and end in different positions, we would say they're actually equal because what matters is their length and their direction.